the first talk is going to be Prashant and I on behalf of the foundation group. We have not from the solution generating team. Okay, so I'm going to start with some of the motivations behind this. So generating novel solutions to solutions is important for a number of reasons. So I'm going to give you just a few of these reasons, but you can kind of think of these as really broad categories. So the first is that even commonly used solutions have a lot of issues. For instance, the care solution that's commonly used has these particularities that you might wish weren't there, or you might wish you had a different analytic solution to get you might want to expand the solution base of the solutions that we know to include more physically realistic solutions. So you might think that there's some kinds of idealizations or abstractions going on, and so having alternative solutions or more solutions to draw on would be useful. And then finally, a lot of these known analytic solutions are used for numerical techniques to benchmark. So suppose that you're doing binary black hole mergers or something like that, and you're using numerical techniques to solve the field equations. You'll use these known analytic solutions to help benchmark your simulation to make sure that you're getting reasonable solutions. Okay, but the field equations are a set of coupled nonlinear second-order PDEs, and that's going to make it quite difficult. So there are a number of known solutions that I'm kind of just listing in this slide, and I've roughly categorized into homological solutions, solutions for depth fluids, and solutions for black. But these are broad. So think of them as capturing these kinds of solutions that can. We have a number of known solutions. That's great here, but we want to expand this solution. Okay, so what are the ways that you can actually do that, expand the solution base? So there's a number of different call them methods, algorithms, general frameworks in which you can expand the solution space to more physically realistic solutions. So I'll list some of them, and again, these are general frameworks, not particular. So you can use, for instance, algebraic classification of the bioconformal tensor, and this is called the Petrov classification. Similarly, you can use algebraic classification of the Ricci tensor, and this is instead of the Petrov classification. The existence and structure of vector fields and symmetry exhibited by the metric. All of these kind of give you ideas of how to think about the classical solutions and then generate them from there. Okay, but among these methods, one stands out, and this is the one that will be the topic of our presentation today. And that is the Newman-Janus, call it a trick, an unboxed algorithm, whatever you want. So it's both very successful and very bad. So I'll read you a few quotes of what people have said. Bambi and Modesta say, in fact, in the original paper, Newman and Janus could not give a true explanation of the procedure. Drayton says vectors say, however, no clear reason has ever been given as to why the Newman-Janus algorithm works, many physicists considering it to be an ad hoc procedure or fluke and not worthy of further investigation. And Del Navarajan in his MA, his master's dissertation, said, no one has fully understood why this method works, and most of consider it an accident trick. Though there are a few that believe it to be a clue to structure. And so it's kind of occupying this strange, it's really successful, but you don't really understand how it works and what it's doing in space. But it is a really great technique for generating new solutions. Yeah, I should have said, happy to take questions.
Okay. So to define a bit what you're calling a solution of general relativity, which equation of general relativity are you referring to, and which you call a solution? Meaning, does it matter? You know,
I'm considering any solution.
So any type of data turns scalars. So it's the four-dimensional fluidity.
Yep.
And there any type of
yeah, typically minimally coupled to gravity. It could be non-linear. Yeah. So that's what we're thinking of. But I think there are also methods that extend beyond that. So in this talk, we'll be focusing on minimally coupled fields, or this original method is minimally coupling fields to matter. There could be non-minimally couplings between the different matter fields, but just the gravity segment.
So that is your general relativity. Then
Yeah.
for solutions, are you going into, find any type of solution, or are you trying to I see. But what is the solution?
For the purposes of this, keeping it pretty specific, so we're saying, suppose you start with a solution and this is how you generate. Suppose you start with a solution, you generate another solution. We're not like I discussed some of the general techniques, but
Yeah, so this has been used to generate naked singularities or wormholes as well. But yeah, you can also do, so we will probably make comments only about black holes, but you should think that it's more general. But we don't exactly know how general it is. That's also something that we want to convey in this. Why it works is a big part of the talk, whether it works. It's like 5 minutes late. Okay, so let me just give you a little background about what this Newman-Janus technique is. So in 1965, Newman-Janus, they wrote down a method to actually compute the Kerr metric or derive the Kerr metric from the Schwarzschild metric. This is an incredible thing to happen because as soon as the Einstein field equations were written, you were able to solve for the Schwarzschild metric within a few months. But to obtain the Kerr metric, doing all the classification and all of that stuff, it took almost half century. So solving for spinning problems is spinning solutions is typically very hard. So to find a simple method that takes you from non-spinning black hole solutions or non-spinning general solutions to spinning solutions is quite like magical, right? It's quite important. So the obvious question that follows is, can we actually do this generally? Can we take any spherically symmetric solution or non-spinning solution and convert it into a spinning solution? So we don't know yet, but we'll just tell you what the state of the art currently is. So this method was immediately applied by Newman, the first author of this paper, to actually obtain the Kerr-Newman metric. So what they did was they considered the charged non-spinning black hole metric, applied the same algorithm, and they actually obtained the charged spinning black hole. So this was the first time the charged spinning black hole was actually, the metric was actually discovered. So it is this method that was used to actually obtain it. So you can get new legitimate solutions. So it's quite exciting that you can probably do this for general cases.
I know.
Oh, thank you. So let me also just tell you what the flavor of the algorithm is, how it works. So we start off the original Newman-Janus algorithm. It starts off from the Schwarzschild metric in Eddington-Finkelstein coordinates, outgoing Eddington-Finkelstein coordinates. These are the metric flows. And just as a reminder, these coordinates are adapted to the outgoing radial null geodesics. So you would, instead of sitting, you just go to a frame in which you're sitting on the photons that is radially going outwards. The metric appears like this to them. And this amounts to a change in the time coordinate from the usual Schwarzschild metric that we are used to seeing to a different time coordinate, which is measuring the change in the length of long photons, essentially. This is how the transmission looks. And these radial null geodesics are also fundamental to the spacetime. There's something called the principal null coordinates, which we'll get in greater detail. The way it works is that the key player in this whole method or algorithm is something called this null tetrad. It's a complex null tetrad. So it's a set of 4 vectors, which are all null vectors. And you can imagine at one point in space, you can construct 4 vectors, which form a basis. And you rewrite everything in terms of the basis of 4 null vectors. The metric you write in terms of all these 4 vectors in this way. And the idea is that we were able to write down these different vector fields explicitly, and just you don't have to follow all the details. I'm just trying to show you what functions turn up in this metric. So the thing I want you to notice is that there's a metric function which is like 1 over r. There's a metric function which is like r squared, and the next part of the trick is going to be very weird, which you will see. So what they then say is that wherever you see a term that looks like 1 over r, you replace it with 1 over r plus r, 1 over r. It's quite arbitrary. So in this step, they've done two bits. They first allowed the radial coordinate to take complex values. So you're saying that your real manifold, your partial metric, which is real, everything is real. First, you lift the radial coordinate to take complex values, and then you do this very weird specific transformation. It just done. It doesn't even end there. You look at the r squared part of the metric that transforms in a different way. It complexifies in a different way. So you use both of these sort of just ad hoc tricks, and when you use this and put it back into your the sort of vector fields that I talked about, you get a Schwarzschild metric which looks complex, which is doing something strange, and then they propose a complex coordinate transformation of this kind, where the radial coordinate takes complex values and the time coordinate also takes complex values. Looks arbitrary. At the end, you just end up with. So this is very weird. This whole setup. You can see that you can say that I will go to complex coordinates. I will do a particular complex coordinate transformation, but none of it is all consistent. It doesn't explain why you're doing this. It just turns out that you get the right answer. You also get solutions, new solutions. But the point is, we don't know why it works. Okay, so again, we just talked about this part being a little ad hoc and arbitrary. So why is this particular set of transformations giving you the curve metric? If you were to take this transformation and do something else here, or this and do something else, would you still end up with the curve metric? So why is it special that these particular things are going to give you the curve metric? And so, for example, you could consider that instead of sending r squared to this r times r bar and then doing the transformation, you were to do something strange like this, would you get the curve metric? And the answer is you would not. So there's also something that is prescriptive about the fact that there are these particular set of ad hoc steps that fit together and it works. So yeah, it's strange.
Okay.
These three transformations consistent with each other, like
No, so yeah.
These two, but this is an
this page, this three.
So the way is there are three steps you can think of. First is you complexify the radial coordinate. Then whenever you see specific metric functions which are dependent on this radial coordinate, you complexify them in certain ways. If you see a 1 over r, this is a function of r, complexified in this way. You see an r squared, you complexify it in this other way. And then separately, you perform a complex coordinate transformation. So these are a series of steps that you can use to go from Schwarzschild to curve. But then, on the next slide, we showed. So this one is doing r squared goes to r times root of r1. So it's a totally different sort of complex equation, and it just doesn't work in this way.
So when you say it doesn't work, you mean that it doesn't give us curve?
That's right.
It does give us something else?
It may. I've not checked explicitly.
Okay.
We just want to throw it on there and say that
Alright.
this does not work. It does not give you curve for sure. There might also be other issues, like for example, the final metric might have pathologies. You might not be able to write down the metric in Boyle-Nyquist coordinates. So we don't know exactly.
I have two questions. First, in the original paper of Newman and Jarris from 1965, did they use the Eddington Finkelstein coordinates? Because Finkelstein, I think he wrote the figure afterwards, I'm not sure. And second, regarding the null tetrad, I think Kerr used that in obtaining his solution, and it was quite complicated when he used it. So and Newman and Jarris were supposed to ease obtaining the Kerr solution and also the charged solutions. So how do they simplify obtaining the other solutions as compared to the Kerr solution if they use the null tetrad method
So
as compared to Kerr?
so the idea
Because
is that,
Kerr's methodology is quite complicated.
yeah, exactly.
He used a Petrov, he used Petrov and also the null tetrad.
Right. So the idea here is that you have a spherically symmetric metric, you start off with a symmetric metric like Schwarzschild. And for that, computing the null tetrad is quite easy. So then you don't actually have to ever do compute the null tetrad for the symmetric case, like Kerr had to. You just do this series of tricks, and then you actually end up with the right null tetrad for the Kerr case. So you don't have to actually derive the Kerr null tetrad like Kerr had to do. So that's the advantage of this trick. So it's extremely powerful, extremely simple, but it just doesn't make sense. Like we don't know why it works.
Yeah,
So
that I know.
yeah.
Nobody knows. Yeah, that I know.
Okay, so in the next section, I'm going to go through some general kinds of explanations that we have given as to contextualize at least why it is. So the questions that we had, remember, are the following. So first, why does using complex coordinates work in the first place? Like, why does that methodology in general work? And second, what is the significance of a particular form of the classification that was used? Okay, so there's been more recent projects that try to address these questions. In particular, we'll be looking at Azure Kaino's method for addressing this question with a modified algorithm. So both of the projects are going to begin with the general form of the metric, not necessarily Schwarzschild, also written in Eddington Biggs 2. So what you do on the Azure Kaino method is that you rewrite the metric in terms of the complex null tetrad. Again, same step. Now you're going to perform a complex coordinate transformation where you're just going to allow R to go to R by theta and U the time to go to U minus by. So note here that we haven't said anything about like the particular form of R and R squared as we had. We leave it quite general. Now you're going to calculate the tetrad length from the above transformation and calculate the inverse metric in terms of the Eddington Biggs coordinates. And the final step is to ensure that the metric that you derive can be put back into Fourier form. What that means is that you have all the diagonal components of the metric and only one off-diagonal term, the GT phi term. So the critical piece of this methodology is that you leave the particular form of the complex coordinate transformation general, like you don't take the form, but B, you ask at the end that it be able to be put back into the Fourier. And it seems, at least from the fact that this is successful, that you're capturing something about why the original worked in the first place. It enabled you to have a metric of the Fourier. Something along these lines is kind of the background explanation. So this is summarizing what I just said. Azure Kaino showed that you don't have to pick a particular complex computation of the R coordinate like Newman and Janus did. Rather, the requirement that we can put the metric into Fourier form seems at least to be.
Yeah. So just on the last slide. So what this also means is that you don't have to do things like 1 over R goes specifically to 1 over R plus 1 over R bar. Separately, when you see a function like R squared that goes as R, you don't have to do these sorts of weird things. You just get the metric functions transformed in the right ways by demanding that you get a Boyle-Implicit from at the end. So this is actually, it gets rid of some parts of the ad hoc nature of the original Newman Janus. Okay, so we've seen that there's some ad hoc bits and you can solve them in some parts of the ad hoc bits that you can also solve in some ways with developments of the Newman Janus algorithm. Here we want to also think about what the uses of having such an algorithm. Can we derive some general results about the space of solutions, or at least the space of solutions that are accessed by this algorithm? So it turns out that you can actually establish very nice theorems of this kind. So the first theorem is on the kinds of perfect fluid solutions that you can generate with the Newman Janus algorithm. So we will just so the theorem says that the only perfect fluid solution that you can generate with this algorithm is the vacuum, which is quite nice. So I'll just sketch the sort of the way the theorem progresses.
Sorry, no matter what source I source there.
Yes, exactly. So what it will turn out is that if you start off with a source that is not a perfect fluid, you will be able to spin it up and get some metric, but it's not going to be the vacuum because you have a source. But if you impose that you are starting off with a perfect fluid, when you spin it up, you will run into inconsistencies as if it's not vacuum. That's the sort of nature of the. So the proof goes somewhat like this. You start off with a seed metric the non-spinning metric that you give to the algorithm. And then it gives you as an output spinning metric. So we note that by G mu. Then with this G mu, the general form of the metric, you can compute the Einstein tensor. And then, so because you have the Einstein field equations, which have to be satisfied, you get this relation between the stress tensor and the Einstein. So now we are asking whether this metric here, for which this is the Einstein tensor, we're asking whether that's consistent with the perfect fluid stress tensor. Means this guy has to look like a perfect fluid, and is this consistent with this guy? That's the question. So the perfect fluid stress tensor in its own rest frame always takes this form. It is diagonal. It has an energy density as its zero component, and then it has a which are all equal in magnitude. This is what we mean by perfect. So when we ask something like this, we want the Einstein tensor by this equation to also have a particular form. When you project the Einstein tensor onto the frame of the fluid, it has to also be diagonal. So that is the main constraint that you get. So, and what you will find is that for a general metric of this kind, there will be two off-diagonal components for the Einstein tensor, the rest frame, which you must demand to be zero. So this gives you two PDEs, and essentially by solving them, you will find rather trivially that the only guy that can satisfy this is that P has to be zero and rho has to be zero. So that's the structure of this argument. So you get nice general results quite simply without having to do all the stuff, like having to start with null tetrads and doing things, deriving things. This is a nice way to obtain such general results.
Okay, so the second theorem that you can pull from this that we want to discuss, and this would be is that the only algebraically special spacetimes generated by this algorithm are Petrov type D. So I'm going to give you a little bit of background to understand what that means.
It's two gotta be true, the theorem, the second theorem, you got a type D, Petrov type D, so. The proof for this.
This is proven in Drake and Cesar's too. And I'm just going to, so here's how you should understand what. So the Weil tensor, which is what is used in the Petrov classification, expresses how the shape of the body that is moving along a due to gets distorted. So compare that to the Ricci tensor, which is going to tell you changes in the volume. The Weil just tells you the distortion. The Petrov classification describes different possible symmetries that this Weil tensor can have. And so the way that you do that is by considering the principle of null direction. This is a direction along which a body will experience no force moving along this direction. And there are four distinct null directions that you can consider with your sometimes, though, these directions can coincide. So an algebraically general spacetime is one for which none of the directions coincide. Algebraically special means that at least two of them coincide. It's possible for three, you could have a 3-1, you could have a 2-2, whatever. But the idea is as soon as any two coincide, you're in an algebraically special. Type D are ones for which two sets coincide, so you only have two pairs. And so the idea here is that you have two coincident directions that define radially ingoing and outgoing null. And there's a separate, it's a separate claim that all black holes of general relativity are type D. And so you might think something like, well, you started with a black hole solution. Maybe it's not that surprising that when you use the Newman-Jennings trick, you're going to stay within the realm of solutions that fall in this type D arena. This is kind of, we're thinking more about how to understand this claim. So it's kind of more working progress. But that's the general. Okay, so in the last part, we want to discuss the responses to the first question. So remember the first question was, why do we think that using complex coordinates would help in the first place? What's useful and why did that? And so one response is given by Gerses and Gersay, and they argue that the success of the Newman-Jennings algorithm, complex translation, comes from the linearity of the field equations for Kershak geometry. And so here's what they say. complex translation is allowed in general relativity whenever you can find a coordinate system in which the pseudo energy momentum tensor vanishes, or the field equations are linear in that system. This is not true for any arbitrary metric, but it is true for algebraically official Harris-Shield metric. And so one way of responding to why did complex coordinate translation seem to help in the first place is to say, well, you're in the special class of metrics. And for that special class of metrics, the linearity is allowing you, or the complex translation is allowing you to exploit the linearity of the equation. And that's why it seems to go. Okay, and the last bit is I want to do some discussion putting this in context with some of what philosophers have said about similar kinds of projects. So during Fraser has this nice paper in which she investigates the use of analytic continuation to relate relativity QFT model to the model. So very different context, but the idea that she is trying to grapple with is similar. So she's asking whether analytic continuation in that context should be thought of as just a mathematical trick. It's not saying anything interesting about the underlying physics. You might think of it like how a coordinate transformation can get rid of coordinate singularity, or whether it seems to teach us something deep about the structural equivalence of the structures that we're dealing with. In the context she's looking at, she argues for the first. She says that this is just a trick. And so the question that I wanted to raise here is, should we say the same thing about the Newman-Janus trick? Is this just a trick that seems to exploit some, mathematical features that don't tell us really anything further deeper about the sound? On the one hand, it seems too strong to say that we've learned anything really deep by using this trick. But on the other hand, the generalizations and like all the explanation slides seem to really tell us something about the structure of the solution space and seem to help guide us in some ways for generating new solutions. And so here's a different kind of proposal by Olivia Patton, where she's looking at a case study from fluid dynamics, and she ends up arguing for a heuristic account of scientific explanation. So what she says is that heuristic aids can enable structural reasoning that informs the search for scientific explanations and the assessment of whether the phenomena are in general agreement theory, especially when you're in novel experiments. Okay, so the claim I want to make is maybe what's going on here is even if the Newman-Janus trick doesn't tell us anything deep, it can play this kind of heuristic role in the reasoning process. So even we can kind of reconcile these two accounts by during Fraser and Patton by saying, well, maybe there's a kind of middle ground where it plays. Oh, so thank you all so much for your attention. Well,
I still don't understand the trick. Of course, I'm not like, thanks, this was great, and I'm just frustrated with myself and with the trick.
No,
Because you had this slide with like the previous explanation by I'm sorry, the person started with
again.
yeah, that just looked like it's really it's really something to do with like particular coordinate transformations, and then the fourth step that's like really satisfying. Oh, it's just a demand on coordinate transformations. But so like at this stage, I was like super happy. Okay, oh maybe it's just a kind of like it's a statement about coordinate transformations. But then I don't know how to square that with the constraints of what I can derive, and then I always end up with technique. That seems to me to be like a fiscal statement, and this seems to be like a statement about coordinates.
Right. So we should
can
clarify.
you help me with this?
We should clarify a little bit. The theorems that we showed were for the original Newman-Janus trick, not the upgrade by Assertion.
I see. Okay.
So this is really a statement about coordinate transformations, right? And the thing is, the way that you can think about it is that the Newman-Janus trick is a very restricted version of this trick. The way to see this is, so what Lynn said earlier was that here we don't do any of this 1 over R goes to this blah 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 all that. What we just ask is that there is a final Boyle-Nyquist form. This is reasonable to assume because there's separately a theorem by Wald that says if you have the metric has some nice properties, etc., you should be able to put it in Boyle-Nyquist form. So therefore, demanding that you should arrive at a Boyle-Nyquist form without any singularity, like without coordinate transformations that are singular, that fixes the metric functions for you. that allows you to avoid doing the 1/r, etc. So, but in special cases, when you had to do the 1/r, let's say this algorithm told you had to do that specific thing, you would reduce the entire Newman Janus algorithm. There's a more general prescription. So that's how you do it. This is not going to ensure that the final space times that you generate are type D. You can get, for example, the Cursian solution from string theory, which is type 1. So you can get all sorts of things. So you're right, it's not giving you physics, it's really a statement about coordinate transformations. It is much more powerful. People generate solutions with this all the time. The legitimate solutions at the end of it, but without this small ad hoc thing. But the ad hoc part is still that you're doing this transformation. And why do you need to use complex coordinates is not clear.
Well, thank you. I had a question about the historical context of what was happening in 65. First, maybe about their own justification of using this step, if there's something that they read themselves in the paper, why they do it, and if it relates to what's happening around that time. Were there other people that were doing complex coordinate transformations in this field at all, or was it something that they drew out of? Where did this come from? Was it a thing that other people were doing around the time? Or was it really something very weird that they introduced then? And the other thing that I wanted to ask is whether you checked in Pittsburgh whether their papers are already archived from them, and whether you could access them to see if they had any correspondences, or whether there's some drafts or things that they were thinking about these things in 1965. I'm not sure if I think they looked it up, they died quite recently, so I'm not sure if the papers are already accessible. That could be very interesting to look at. They have some correspondence.
I mean, I think if they did have an explanation, it would be like more broadly known. So I think
Okay.
I have to look at it, but feel pretty okay saying that they had a good explanation. They certainly didn't.
No, but justification, is that the same thing? I'm not sure, but did they have a justification?
No, I mean, the justification was just that.
Well, it could be that there was something else going on, or that they had an analog or some example.
So I have a couple of problems with that. First is that this is speculation. So Newman and Penrose in 1962 or something, they were working with these null tetrads quite heavily. And they were doing spinor formalism, all of this. That's how they defined the Bondi radiation, like how you measure gravitational waves. So now you're looking at these null tetrads all the time. You're trying to cast things. And I assume, like, as soon as they saw Kerr's paper in 1965, they looked at the null tetrads and all that, and they looked at the Schwarzschild null tetrads, and they just found this trick. That's one speculative argument. Another is that if you write things in Schwarzschild coordinates, the structure of the metric has the vorticity, I think, in the metric itself. So that actually looks remarkably simple. So in Kerr it looks like 1/r, and in Boyle it looks in Schwarzschild looks like 1/r, and in like Kerr it looks like r squared plus a squared plus squared theta. So really you can sort of think, here you start to see some things. I don't know. So that's probably what it was. But they're excellent relativists, and in the original paper they said this is a derivation. The paper they say it's inside in quotes. We don't know why this works. It's just a thing, but it does give you the right answer. And also people have worked on trying to understand why this works. They've done a bunch of things. There's books on complex spacetimes, trying to understand whether you can imagine Schwarzschild as a real slice of a complex manifold, and things like this, but this is still open.
And was that quite recently that people started to work on that?
No, this is
That was much.
Yeah, so this book, for example, was written in 1972 by Flaherty. So it was 7 years after. People are working aggressively on this.
Yeah.
And this Zetteri's paper is also 2000. There's the Azrek paper from 2014. So people are still, I have a paper like last month on something similar. So we've been sort of, it's a very important part to understand why this works.
And this paper opened that field to think about that.
Absolutely. Yeah, exactly.